All right, friends and neighbors, welcome back. Today we are doing Chapter 14 of the CCNA, analyzing existing subnets. And so we're going to go through a lot of subnet examples, and then I'll help you do a table. So in this video, the exam topic is network fundamentals, right? Configure and verify IPv4 addressing and subnetting. So in this collection of things, we're going to do subnet IDs. We're going to take a look at the subnet broadcast addressing, and then the range of possible and usable addresses, all from being given an IP address and then the mask. So then we'll do the "Do you know this already?" questions. I think I like the idea of putting them at the end. It seems to be working out all right. And then we'll do a look ahead to Chapter 15, which is subnet design. Right. So you are given a problem. What subnet should go along with it? Well, what is a subnet? When we want to define a subnet, we have to realize that a subnet behaves exactly like a regular network, right? So it has a range of addresses, it has a mask. Everybody in the subnet shares the mask. Typically, they all share a router, they all share a broadcast address, right? The only thing that's a little bit different is that it's part of a class-full address space. Now that also means we can get into some funny masks, right? The way that we break up a class-full address space is by manipulating the mask. And we do that by stealing bits of the host bits, or the host-specific portion, right? The suffix. And the easiest way to look at that is the binary. Now, there are some shortcuts, right? We did some last time. We'll do a couple today. So there are some shortcuts, but I personally always like to rely on the binary because it makes life much easier if you understand what's going on there. And no matter how difficult the problem, you can solve it by looking at the binary. Okay, now in a subnet, we're talking about consecutive address numbers. So this is true for in two cases, right? So if I break up a space into a bunch of subnets, then the subnets themselves are going to be sequential. And then the addresses within the subnets are going to be sequential as well. So if you put that all together, one subnet's address space goes right into the next, goes right into the next. Now, when you take a look at the host bits, right, that tells you how many hosts are available in each subnet. So you break up an address space, right, a class-full address space into subnets, and then you look at how many host bits are left over. That tells you how many possible addresses are there. The lowest possible address is the subnet ID. The highest possible address is the broadcast address at that particular subnet. Now in binary, if you take the host portion, the suffix, and you put all zeros there, that's the subnet ID. If you take the host portion and put all ones there, that's the broadcast address. Works every single time. I'll show you some examples. But that's how you figure out what your range of possible addresses are. The rest of the addresses are unicast host addresses, meaning that you assign them to one particular node, and that's it. And so we can't use the lowest, we can't use the highest, 2 to the h minus 2. That's why it works out that way. Now there's an example in the book. You are given an IP address, 172.16.150.41, but then you're given this mask of 255.255.192.0. So the way that we start this problem is we say, okay, that would normally look like a Class B network. And so you would say, in a Class B, we have 16 host bits, and therefore 65,536 possible addresses, 65,534 usable addresses. But this has been subnetted. And we know that's been subnetted because we look in the third octet and we see this doggone 192 here. And so if we break this out into binary, we can see what that actually means is that 2 of the host bits were changed to 1s. So that means we stole 2 bits. Now, how many possibilities are there in 2 bits? Well, there are 4. 0, 0, 0, 1, 1, 0, and 1, 1. So there are 4 possibilities. That means that we created 4 subnets when we did that. Now, another way to think about that is how many bits are in the subnet field? Well, there are 2. 2 raised to the second power is 4. So whatever way you want to think about that, that is how you would arrive at 4 subnets. Now, if you don't mess around with the subnets at all, that means they're going to be of equal size. Now, right away, you can always find the subnet for a particular host if you AND the host's IP address with the host's mask. So that's what I've done below here. So this is 172.16.150.41 broken out into binary. And then here's the mask broken up into binary. And what we find out when we do the ANDing process, that the network that upon which this host resides is actually 172.16.128.0. So that's the subnet. You would never get that by just looking at the IP address. Now, is it possible to get it from some other way? Well, yeah. So let's take a look at something else. And the hint that I'll give you is that if we start with the number of host addresses in the class full address space, and we simply divide it by 4, that means each one of the subnets has 16,384 possible addresses in that subnet. So we're going to start there, right? I had 65,536. I divide it by 4. I get 16,384. Now this also means that I have 14 bits of addresses for the host. Take a wild guess what happens when you go 2 to the 14th. You get 16,384. Now in the book, he also talks about this number line analogy, where if you lined up all of the addresses and in the first subnet, you started counting, and then you went to the next subnet and you just kept counting, and then you went to the next subnet and you just kept counting. Eventually you would get through the entirety of the class full address space. You have to remember that we start counting at 0. So the first address in all of these subnets would be 172.16.0.0. So if we do that, and we say, okay, the first address in the first subnet is 172.16.0.0, and then we add to that 16,383, because we're going to start counting at 0, so the entirety is 16,384. Then what I'm going to do is just convert 16,383 to binary. And that's what it is right there. It's just 14 bits of all ones. Well, if I break that into dotted decimal notation, what I actually get is 172.16.63.255. So the range of addresses is 172.16.00 to 172.16.63.255. Now to get to the next subnet, I just add 1 to that. So the next subnet would begin at 172.16.64.0. So that's the number line analogy, right? Whatever the last number is, add 1 and I start the next subnet. So let's do the same thing. We'll add 16,383 to that. Converting that to binary, what that actually is 172.16.64.0 to 172.16.127.255. We repeat that again, and we go 172.16.128.0, right? We added 1, plus 16,383, so we get 172.16.128.0 to 172.16.191.255. Now we're coming into our last subnet, so we add 1, and what we should wind up with when we're all done is the last possible address, not only for the subnet, but for the class full address space. So 172.16.192.0 plus 16,383 gives us that range all the way up. And so that worked out. Now we could stop talking right there. So far we've seen 2 ways to figure this out. But what if there was another way? It turns out that there is. This happens to be my favorite way of doing it because it's binary and it can't steer you wrong. Looking at this another way, what we're going to do is examine that subnet field, and we're going to go through the binary possibilities. We know that the address space starts in the 172.16.0.0. So that's this one right here. And look at the subnet field. It's 00. We're going to copy this down here, but all we're going to do is change the subnet field to 01, 10, and and 1, 1. And what this does is it gives us the subnet IDs. Why? Because we're also going to put all zeros in the host portion. This gives us the lowest address in each possible subnet. In other words, it gives us the subnet IDs of 172.16.00, 64.0, 128.0, and 192.0. What if we take the host portion and do the exact same thing, but we convert the host portion to all ones now? So same thing with the subnet field, but all ones in the host portion. So in the first subnet, we started 16.0.0. We put in all ones, which is exactly what we did when we converted 16.383 to binary. And we find out that we get 172.16.63.255. So here we've done this a third way, and we've just gotten the same answers each time. We do it again with the second subnet, we get 127.255. Third subnet, 191.255, and the last subnet, 255.255 in the end octets. So there you go. So this is the binary method, but you can use whatever way makes sense to you to get to the end here. Well, what else do we know about these subnets? Well, we just filled in all zeros for the host portion, and then we filled in all ones in the host portion. And what that did was it gave us the subnet ID and the broadcast addresses, right? The lowest possible and the highest possible, the subnet ID and the broadcast ID. Now, all the rest of the addresses in the subnets are going to be assigned to host. They're going to be the unicast addresses for host. Well, how do we figure out what's usable? We know that it's 2 less than the possible. So all that we're going to do is take the lowest possible address and add 1. And that'll give us the starting range of the usable addresses. And then we go all the way to the top, and we take the highest possible address in the subnet, and we subtract 1. And that's our range. So in the first subnet, 172.16.00, we know that if we just add 1, then we get 172.16.01. That is the beginning of the usable host addresses. The broadcast address for this subnet is 63.255. We subtract 1, 63.254, and that gives us our range of possible addresses. And if we counted all those, it would be 16,382. And we can see we've done the exact same thing with the other subnets, right? We just add 1 to the lowest and subtract 1 from the highest. Now you could do this exact same exercise with binary, right? If you broke all of these out into binary and you took, for example, 172.16.128.0 and you broke that into binary and then you just added 1 to it, you would get 128.1. And if you took 172.16.191.255, put that all in binary, and then just subtracted 1 from that, you would get 254. So that's the subnet ID for each one. It's the broadcast address for each one, and it is the range of usable host addresses for each one of these subnets. But here's a fun question to think about. Where would your routers be? Well, there's a convention that most organizations follow, and they either pick addresses that are high in the range or low in the range of usable addresses. So it wouldn't be unusual at all to say that all of the routers would be all of those 254 addresses. But some folks like to put their routers at the very beginning of the address space, so it wouldn't be strange to see .1s everywhere. Well, this all seems very challenging, very difficult. Do you have to know how subnets and how masks work? And the answer is absolutely. Now, there are subnet calculators out there, but you have to start the process somewhere. And the reason that you have to know them is they're used everywhere. An IP packet itself doesn't carry a mask, right? So you're not going to be able to look at an IP packet and say, oh, I know what network you're part of or where you're going or what I have to do to get you there. But all of the devices in the path make decisions based on the networks and based on the masks. So your host configuration has a mask, whether you got your IP address statically or via DHCP. The host routing table has a mask in every single line. Router configurations, IP addresses have masks. Routing protocols themselves use masks, and those masks are actually in the routing protocol header. And then, of course, router routing tables have masks in them as well. By the way, it gets a lot more fun later on. We're talking about subnetting. We're talking about breaking up address space. But what if I said we're going to glue address space together? That's aggregation or supernetting. And then pushing that even farther, you can have an organization that uses subnet masks of a particular length in one place and a completely different size subnet mask someplace else within the same organization. Okay, let's do some tough examples. Now this is table 1410 in the book. I've added a little bit to this, right? So in 1410, it just gives you the IP address and then the mask. And what you have to do is figure out what the subnet ID is for this particular IP address. And they're challenging because they're goofy masks, right? So what I've done here is I've taken and highlighted where all the action is. We don't really care about this in this first one, the first octet. It's just going to be 10. So I took 77 here and 248, and I broke them both into binary. All that we're going to do is AND these two together. And so what we find out is we get a mask that looks, or I'm sorry, we get a result that looks something like this. So what is this value now? So this value turns out to be, we get 64, 32, no, 16, no. So it's 64 plus 8, or 72. So we would wind up on a subnet of 10.72.0.0. Okay, so if you followed along with that one, let's tackle the next one. So the action in this one, right, we got a goofy mask right here, and that is in the third octet. So here's 99 in binary, and here is 192 in binary. If we do the ANDing, we get a mask that looks like this. Right now, remember that anything ended with a 0 gives you a 0. So we got, it looks like we ought to have ones here, but we don't, because we're going to end with all these zeros. So that is our final result, which means that our new network here, or the subnet upon which this node resides, is 172.30.64.0. Whoops. Then in there, right, 172.64.0. Well, let's keep going. In this last one, it looks like we're subnetting a class C network, and the action is over here in the last octet. Here is 54 broken into binary, and here is the mask, 252. By the way, I included this table over here, so if you steal 1 bit, 2 bit, 3 bit, 4 bit like that, then this is what your pattern is going to be in the octet where the subnetting is happening. All right, so if we do the ANDing again here, the last two are going to be 0. We got to make sure we remember that. So we go 0, 0, 1, 1, 0, 1, 0, 0. Well, let's see what this works out to be. That looks like 32 plus 16, 48 plus 4, 52. So we're going to go 192, 168, 6.52. And then we've got this next one where the action is in the third octet, right? So here is the binary. Whoops, let's fix that one. So when we do the ANDing here, there's 3 in binary and there's 128 in binary. What we get here is all zeros. So that means the subnet for this one is actually 10.77.0.0. So it looks like, it sort of looks like a class A, then it sort of looks like a class B. But what we just have to realize is that this is actually subnetting into the third octet. So this is actually creating 512 subnets. And this host just happens to live on the 10.77.0.0 subnet. So here we have 55. And then the mask is 254 in the third octet. And so if we do the ANDing here, we get, there we go. Now that looks a lot like the one that we did earlier. It's just a different octet. So again, 48 plus 4 is 52, and then we go 54. So the answer here is 172. What is that? 2254.0. Okay, let's do this last one. Here the action again is in the last octet. We've got a 248 here. So 76 in binary looks like that. And then we've got this 248. So if we do our ANDing again, we get 0, 1, 0, 0, 1, and then 3 zeros. So this address space is going to be 1.99.53. And then our last octet is going to be 64 plus 8, or 72. Now there's a couple of things that will help you. They're just sort of sanity checks when you look at this. First of all, the subnet ID will always be lower numerically than the IP address, right? Because we don't assign the subnet ID to a host, so the host will always have a higher address. So for example, if we look at this one, we go 1072.00. Oh, that is in fact lower than 1077.55. The other thing that's a sanity check is that we want to make sure that these are subnet addresses, which means that they have all zeros in the host portion. So if you wind up with an odd number, for example, in the last octet, then you've made an oops somewhere. So this looks very much like a subnet ID. This looks like a subnet ID. What is going on with this one? Well, remember that 52 in binary has all zeros in whatever's left of the host portion. Well, that doesn't seem like much of a host portion. But if you steal 6 bits into the host portion, right, then you're only going to have a couple of bits left over. Now, these are very small subnets, right? In this particular case, these subnets just have a couple of addresses in them. And that's legal. It's wasteful, but it's legal. So you just have to remember that. So if something looks a little strange, just check to make sure that the host bits are 0. Now, the other thing that can throw you is if you have something other than zeros in the base 10 numbers, right? So this is 52, this is 72, and that looks strange. That can't possibly be a subnet address, but it is, right? Because remember that we're breaking space up inside of an octet. So they do not have to be nice clean zeros like these are here. So here are the did you know this already questions. If you examined all of the addresses in one subnet in binary, which of the following would be correct about the parts that would be equal? Remember that if all of the nodes are in a particular subnet, the only thing that would change for each node would be their host address in binary. In a subnet, that subnet field would be the same for everybody, and so would the network. So the answer was D. Number 2, which of the following is true regarding the binary subnet ID, subnet broadcast, and the host IP address values? Choose 2. Well, now we know the answer to this question, right? If we're talking about the subnet ID, we know that the host portion is going to be all zeros. And if we're talking about host IP addresses, they must not be zeros. So that was the answer there was B and D. Now, if we want to push this a little bit farther, we would know that the broadcast address would be all ones in the host portion. Number 3, which of the following is the resident subnet ID for the IP address 10.7.99.133? Well, for this one, you would just know that the mask would actually be 255.255.255.0. And if you did the ANDing, it would zero out the last octet. So this one is actually pretty straightforward, 10.7.99.0. Which of the following is the resident subnet ID for the IP address 192.168.44.97/30? Now the trick here is that /30. What does /30 look like? Right, that is 6 bits in the last octet, right? So these are very, very, very small subnets. So if you converted 97 to binary and then you put a mask underneath there that was 6 bits with 2 zeros, that last digit would be zeroed out, giving us 96. Number 5, which of the following is the subnet broadcast address for the subnet in which the IP address 172.31.77.201 resides? Now, the tricky part there is that's /27, right? So you figure out what the host bit's size is, how many bits are left in the host portion. Well, we know that if the host portion is only 5 bits, and we put all ones there, then that would give us 223 on the outside. And maybe this one's actually worth doing on our spreadsheet. So if we take 172, 31, 77, 201, and we take a look at what the mask is, right? So that mask would actually be, right? So that would be our mask. Now we take a look at where all the action is happening. It's happening in that last octet. Well, what does that last octet look like? Well, 201 converted to binary, 128, 192, we need 9 more. Okay, so not 32, not 16, there's 8. There we go. And then if we take a look at the binary for the mask, it would be this. And maybe we'll do the ANDing right here. So if I do this ANDing process, then I would get a network that looks like this. I would get 1 1 0 0 0 0 0 0. Well, what is this address? This is the 192 network. Well, what if so we can see all zeros in the host portion here, right? So there's our host portion. And so that means that my subnet here is 172, 31, 77, 192. Well, what would the broadcast be? We need to take this exact same ending and put all ones in the host portion. So that would look something like this. Well, what is this value? Turns out it's 172, 31, 77 dot, well, what's 192 plus 31? Turns out it's 223. So that's how you would work through that problem. That was a tough one, so I thought we'd do it here. So this last one is a little bit of a design problem. You are building a DHCP server, and we need a DHCP scope that contains that provides the last 100 usable IP addresses in the network. Now, the first time I looked at this, I was like, oh, this is pretty easy. But what we want is the last possible addresses in the subnet and specifically the last 100. So if we figure out what the range might be, then we're in much better shape and we can see which one of the answers would appear in the last 100. So it turns out that if you're a /23, then the network is actually 4.0. 10.1.4.0 is the network, right? And then in that subnet, you have a big address space. So the address space for this subnet is actually 4.0 to 5.255. And so an address that would appear in the last 100 would be 5.200. Our Chapter 15 look ahead is that we're actually going to do subnet designs. This is where you're given a problem or a network and say, all right, what do you want to do with your subnets? Can you choose the right mask for the problem? So that means that you want to know or be able to figure out the right size of the subnets, the range of hosts, the correct number of hosts for each subnet, and then be able to find them all, find all the patterns that we need, and we'll work with binary again, but we'll be starting at a different point. Now that we get subnets, now we get how to find the range, and we get the binary, can we apply that knowledge to a given problem? Okay, this has been analyzing existing subnets. So the basic problem that we're given in this one is, given an IP address and a mask, can you find out the network? And if you can find out the network, can you find out the range of possible hosts on that network? And therefore, can you find out the subnet ID? Can you figure out the broadcast? And once you figure those out, can you figure out the usable addresses in there? Now, there are lots and lots of challenging problems in this space, but usually working with binary when things get tough solves most of your problems. All you have to do to get that range is figure out the subnet mask said, here's my host portion. Put all zeros there and then put all ones there. That's your possible range. and then you can work out the usable range from there. And we know that coming up, can you figure out what the subnets ought to be given a particular problem or scenario? Thanks for watching. Thanks for listening. Like and subscribe if you're enjoying the content, if it's helping you through. No matter how big or small or complex your subnets are, may those packets always reach their destinations. And remember, this is CCNA. You can do this.